All right, so I'm actually going to make a video where I talk about homework 1. I haven't graded yet. I'm going to grade it momentarily. Um, so the first one was just you wanted a vertex for every subset of the set 1, 2, 3, and there are 8 subsets. Um, so here I have 8 vertices, and each vertex has a name, and the names are just subsets of the set 1, 2, 3. Of course, it's a subset of itself, so there's a vertex whose name is the entire set, but there's also vertices for every possible subset. And just to try to do this in an organized way, I put the largest ones on top and then the smallest ones on bottom. So there's one subset with 3 elements, and then down here I have all the subsets with 2 elements. Here's all the subsets with 1 element, and then here's the subset with 0 elements, which is just the empty set. And vertices are supposed to be adjacent if they correspond to sets that are disjoint. So, for example, this vertex and this vertex are adjacent because this set and this set are disjoint. So I'm not going to go through the whole thing. You just have to go through and find all the pairs of disjoint sets and make sure you draw an edge from between each one. Yeah, so that's number 2. For the next one, there was a part A and a part B, and the instructions are that you're given 2 graphs and you're supposed to determine whether they're isomorphic. The first 2, as it turns out, are isomorphic. When I did this one, I had to stare at it for a while. I tried to think of a few reasons why they wouldn't be isomorphic, but then I couldn't think of anything, and then I said, well, maybe that means they are isomorphic. So I started trying to come up with an isomorphism. So here I have an explicit isomorphism that you can check, but really maybe the more helpful way is to try to do this visually, if this makes sense. And this graph and this graph, they kind of look well, they look similar, right? They're sort of, if I look around the outside, they're arranged as a diamond. And so, for example, it's tempting to say that W can correspond to 1 and U can correspond to 3, because this is like the vertex on the left and the vertex on the right. But that won't work. For example, if you look at W and U, they have 3 neighbors in common, W and U. They're both neighbors of T, they're both neighbors of Y, and they're both neighbors of V. If I wanted W and U to correspond to 1 and 3, then they should have exactly 3 neighbors in common. But actually, if you look at the vertices 1 and 3, they have 2 in common, they have 7 in common, 5, and 4. So if there's going to be an isomorphism, all that means is that W and U can't correspond to 1 and 3, like this. So then you have to think of other possibilities. And what ends up working is you're sort of visually turning it sideways. So W and U, yeah, let me try to do a better job of explaining this. We have, here goes. What I did to really visualize this is I want to take this picture, turn it sideways, and pull the X and the Z out. So I want to move Z maybe out here, and Z is still going to be adjacent to T and V. And I'm going to move X out here, and X is still going to be adjacent to T and V. And then I'm going to turn that picture sideways, and it looks like this. So that's my attempt to explain visually how you can see this isomorphism. Of course, you can always just check that this correspondence is an isomorphism. And when I say check, I mean like, well, T and V are not adjacent in this graph. And then so 1 and 3 should not be adjacent in this graph, and so they aren't. And you can check all the all the pairs that are supposed to be adjacent correspond to pairs that are adjacent here, and if they're not adjacent, then they correspond to pairs that are not adjacent. In any case, they are isomorphic, and this is an isomorphism. For part 7b, they are not isomorphic, and there's an easy reason why. The easiest reason is that they just have different numbers of vertices. So yeah, let's talk about 19. So in 19, we know that we have a bipartite graph. It has partition U and W. So I mean, this isn't really a picture of a graph, but I just drew two bubbles, and you can imagine a graph where all the edges have one end in U and the other end in W, because it's a bipartite graph, and that's the partition. We're told that U has 10 vertices of degree 6, and we're told that U has 4 vertices of degree 2, 3 vertices of degree 4, and then some unknown number of vertices of degree 8. So what we're going to do is basically this is like a handshake lemma type stuff. They're giving us information about the degrees in a graph, and we know that if we add up all the degrees, then we get 2 times the number of edges. However, for this one, we need to make the following observation. And this is an observation about bipartite graphs that's, it's like more specific than the handshaking lemma. In a bipartite graph, once again, every edge has one end in U and the other end in W. And so if I want to count the number of edges, one thing I can do is just add up all the degrees of vertices in U, right? Because every edge in the entire graph has one end in U, so I will count every edge exactly once if I just add up all the vertices in U. Similarly, I could just add up all the degrees of vertices in W, and that would also count every edge exactly once, because every edge has one end in W. So like I said, this is more specific than the handshake lemma. The handshake lemma says that if I add up all the degrees in both sets, then I get 2 times the number of edges. And this is more specific, because this is saying if I just add up all these, I get the number of edges. And then if I add up all of these, then I also get the number of edges. And of course, that implies the handshaking lemma, because if I added up all of them, then I would get twice the number of edges. Anyway, that's what we're going to do here. And we're going to do it from both sides. If I want to count the number of edges by adding up the degrees of vertices in U, then I'm going to write this sum. And that's going to be 10 times 6, because we know that U has 10 vertices of degree 6. So if I'm adding up the vertices of the degrees of vertices in U, I get 6 plus 6 plus 6 10 times. So 10 times 6. Of course, that should be the same as if I added up all the degrees in W. And if I do that, based on the information I have 4 vertices of degree 2, I've got 3 vertices of degree 4, and then some unknown number of vertices of degree 8. So let's say that I have X of those. And so this gives me an equation, 60 equals this plus 8x. So I get an equation, I solve for x, and then the question was the order of G. So it's the total number of vertices in G. So if I add these up, well, there were 10 vertices in U, and then out of the vertices in W, there were 4 of them that had degree 2. There were 3 of them that had degree 4, and then there were X of them that had degree 8, and X was 5, so I'm adding all this up, and I get 22. Okay. Let's talk about the next one, which this one was probably the most work. It's safe to say, I think, the most work. So this is about graphs where both G and G complement are bipartite. So I'm going to start with a simple observation that's going to limit the number of cases that we have to look at. So here's the simple observation. If I'm talking about a graph G and its complement is bipartite, G and its complement are both bipartite, then if I look at the partition for G, I can't have a set of size 3 or more. And here's the argument. If G has partite sets A and B, and maybe say one of them, say A, has at least 3 vertices, then what happens when you take the complement? A is one of the partite sets in G, meaning that G doesn't have any edges with both ends in A. That means G complement would have all possible edges with both ends in A. So like, maybe I'll draw something up here. In G, looks like this. A has 3 or more vertices, and none of these are adjacent to each other in G. Meaning in G complement, all of these are going to be adjacent to each other. And so that's what I wrote here. But that would mean that you have a triangle in G complement, because you have 3 or more vertices in G complement, and they would all be adjacent to each other. And that's not possible. G complement can't have a triangle and be bipartite. So that's not possible. In other words, it's not possible for the set A to be 3 or more. So A would have to be 2 or less. Similarly, B would have to be 2 or less for entirely the same reason. If B had 3 vertices, then in G complement they would all be adjacent, and you'd have a triangle. So that's good. This goes a long way. There's still a significant amount of work to be done, but this is good. This means that if whatever G is, the set A has at most 2 vertices, and the set B has at most 2 vertices. Also, what we're going to do is we're going to consider several cases, and to limit the number of cases, I would like to say, without loss of generality, that's what this abbreviation means, we can assume that the size of A is less than or equal to the size of B. This is just a fact that if a graph is bipartite, that basically means you can partition the vertices into 2 sets and all the edges go from one set to the other. It doesn't really matter which set you call A and which set you call B. You can switch the names of the 2 sets, and that still gives you a valid partition of a bipartite graph. So if it doesn't really matter which one we call A and which one we call B, we might as well just say that A is the name of the smaller one, or if it's a tie, well, yeah, it could be a tie, they could be the same size. Otherwise, we'll assume that A is the smaller one. Okay, then we start running through some cases. So in this class and in this book, we don't talk about graphs with 0 vertices. The smallest number of vertices a graph can have is 1. So the smallest case would be when we have exactly 1 vertex, and if we're assuming that A is smaller than B, or size of A is less than or equal to the size of B, then it would have to be 0 here and 1 here. And graphs with 1 vertex are not too exciting. There's really essentially just the one graph. Like, you have your 1 vertex, and you can't even have any edges. You would need 2 vertices to even have an edge. So it's just this lonely vertex. And what does the complement of this graph look like? Well, it's this, because there's no possible edges. So there's really nothing happening here. So this is a graph, and this is its complement. They're both bipartite, because, right, I mean, A is the empty set, and B is this set, and there are no edges with both ends in A or both ends in B, so that's enough. That's bipartite. And similarly, of course, this is the same exact graph, so they're both bipartite. Okay, so that's a case, and then let's slowly start talking about larger numbers of vertices. So I'm going to keep it with the size of B is just 1, and what if the size of A is 1 instead of 0 now? So now we're talking about graphs with 2 vertices. There's essentially just 2 graphs that have 2 vertices. There's this graph and this graph. Either you have the edge or you don't. They are both bipartite. I could call this set A and this set B, and once again, there's no edges with both ends in A, and there's no edges with both ends in B, so this is bipartite. Similarly here, I can call this A and this B, and this is bipartite. What else? So at this point, we've covered all possibilities where the size of B is 1. Keep in mind that the size of A is less than or equal to the size of B, so if B is 1, then A can either be 0 or 1, and we covered those possibilities, and we drew every possible graph that was like that. So now we've got to move on to size of B is 2. And so that means size of A could be 0 or 1 or 2. And once we consider all those cases, we'll be done, because we know that none of these are going to get bigger than 2. That's not possible. We already covered that. So what do these graphs look like? Well, it's kind of weird when you have a set of size 0. It's okay. It just means that A is the empty set, and then B is a set of size 2. So this is kind of the only way that G could look in this case. Right? I'm not allowed to draw this edge because there's not supposed to be any edges within B. So this is really the only graph that could be described by this. And its complement looks like this. By the way, this is bipartite. Of course, I would have to make these 2 sets the partition. But that's okay. Oops, I didn't mean to write G prime. I meant to write G complement in these places. But yeah, so what I was saying was G complement can be bipartite, and the bipartition can be different from the partition in G. Right? In G, these 2 vertices were in the same set. They were both in B. But in G complement, they're in different sets. But that's okay. I can call these like A prime and B prime. And A prime, B prime is a partition of G complement. But let me point something out. This case that we just talked about was actually already covered above. These are the same graphs. Like this This is just two different ways of looking at the same graph. Up here, we were looking at the graph with two vertices and no edges, but we were viewing it as a bipartite graph where this is A and this is B. Down here, we're looking at the same graph, actually. We thought it might be different for a moment because we were looking at it differently, like A was the empty set and B was the set of both vertices. But in the end, this graph and this graph are the same. It's just the graph that has two vertices and no edges. So we're not going to list, even though this is a valid thing, like this graph and this graph are both bipartite, we're not going to list it as a separate answer because we're already putting this one on the list. In the end, I'm going to make a list of all the graphs that worked. And so we won't list anything twice. Where does that put us? So we just covered when size of A is 0 and B is 2. So now it's time for when A is 1 and B is 2. So what can it look like? And now I'm touching on a little bit of what I touched on in the video that I made, just explaining what this problem means. Here's a possible graph where A has one vertex and B has two vertices. And this is just the possibility where you don't have any edges at all. And the complement of that would be a triangle, which is not bipartite. There's another possibility, though. I could have, say, one of the edges going from A to B. And I think I covered this in the previous video as well, but the complement of this graph would be this graph. And this one is bipartite. It's not with this partition, but say if maybe I'll do this in red. If I call like this set A prime and this set with just this vertex B prime, that's a bipartition of this graph. And what I'm going to say now is we have essentially covered all of the cases here, where A has one vertex and B has two vertices. Let me explain that a bit better. The largest possible number of edges you could have is 2. Like you could have 0 vertices like this picture looks, you could have one vertex like this picture looks, or you could have this edge and this edge, and that would be 2 vertices. Now, when I put my final answer down, these graphs, they come in pairs naturally. Because we're talking about graphs G that are bipartite such that G complement is also bipartite. So the graphs that do that sort of naturally come in pairs, and let me explain, like these two graphs are a pair. They're complements of each other and they're both bipartite. So when I put my final answer, I'm not going to put down either of these graphs because this is a pair of complements, but they aren't both bipartite. This one is and this one isn't. But I am going to put down this pair. And what I'm pointing out is that this pair includes both the graph that has one edge and the graph that has two edges. And that's all the possibilities. When you have 3 vertices, you can either have no edges like this one, you can have one edge like this one, you can have 2 edges like this one, or 3 edges like this one. And we've covered all of those at this point. This pair is the only pair that works. Okay. Almost getting close to done here. The last thing we have to do is consider the graphs where A has two vertices and B has two vertices. And I'm going to try to be organized about this. I'm going to start with the smallest possible number of edges, which is 0. So the graph would just look like this. And then, of course, that means the complement would have all possible edges. It would have this. And this is clearly not bipartite. For example, I can see a triangle here. I mean, there's triangles all over the place, actually. So I'm not going to put either of these graphs on my final list. Okay, now let's talk about the possibility where G has just one edge. So it's like this. And then the complement would look like this, and this is still not bipartite, it has a triangle. So, and this is important, there's essentially only one way to draw one edge. You could say, well, what if I had drawn this edge instead of that edge? But if I'd drawn this edge instead of that edge, the graph that I drew would be isomorphic to the original one. Right? Because if I drew this edge instead of that edge, that's just like if I had said, let's flip these two vertices and flip these two vertices. And so I wouldn't be getting an essentially different graph. It would be essentially the same graph because it would be isomorphic. So there's really just one way to draw one edge. Now, what am I getting at when I say that? Now we have to consider the possibilities where there's two edges from A to B. There are multiple ways of drawing two edges from A to B. It can look like this, or it can look like this. Those are essentially the two ways. In other words, the two edges that I draw could be touching each other like this, or they could be not touching each other like this. And we'll consider them separately. If I do it like this, then the complement is this, and that has a triangle, so it's not bipartite. If I draw it like this, then the complement is this, and this is bipartite. Actually, yeah, okay. Again, I drew these bubbles, but these bubbles are not the partition for this graph. This graph is bipartite, but these bubbles are not the partition. Let me draw it. If I call this A prime and this B prime, that is a bipartition because there's no edge with both ends in A prime and there's no edge with both ends in B prime. So this pair of graphs is going to go on my list. They're both bipartite. And those are the ways to draw two edges. So we move on. Now I have to draw three edges from A to B. And there's essentially only one way to draw three edges. Of course, the largest possible number of edges from A to B would be 4. There's 4 possible edges from A to B. So if I'm drawing 3 of them, then basically that just means there's one of them that I'm leaving out. So there's really just essentially just one way to do it. So here's one way to draw this. And then if I do the complement, I get this. And of course, I drew these same bubbles, which these are no longer a valid bipartition, but this is a valid bipartition. Finally, there's the possibility with all 4 edges. That's when G looks like this, and then G complement would look like this. Actually, so this is a pair that would seem to work, and again, this one's bipartite because I can call this A prime and B prime. So this would seem, this worked, but let me point out that we already covered this. This pair of graphs is the same as this pair of graphs up here, right? This one is isomorphic to this one, and this one is isomorphic to this one. So even though this worked, this isn't, we don't really need to put it on the list if we're already putting this on the list. Okay, so let's put it together. What did we get? We got the boring graph that only has one vertex, so that's this one. And like I said, okay, I kept saying they come in pairs, but sometimes they're both the same, like it can be paired off with itself. This and this are the same graph, so I'm not gonna put that twice. I'm just gonna put that once. Then there's the graphs with two vertices. There's this one and this one. So here and here. Then there's the graphs with three vertices. And if you remember, there was, wait, oh, no. This was still when there was two vertices. But we said that this one was isomorphic to this one, so we don't need to list it again. Then there was the graphs with three vertices. This pair was no good. This pair was good. So that's here and here. Then there's the graphs with four vertices where it was like 2 and 2. So this pair didn't work. This didn't work. This didn't work. This did work. So I listed those here and here. And by the way, so this one clearly looks just like this. Actually, can I just pull out a little bit? Yeah. Yeah, so the graph in the top left and the bottom left are the same. But what about this graph? Whoops. What about this graph and this graph? They're isomorphic. I just chose to draw it in a better way. This graph is really 4 vertices all in a cycle. You can go around all 4. It's just that the cycle is kind of twisted, so there's this X in the middle. I just untwisted it for the drawing. I wanted to draw these in a clean way. So there was this one, and then there was this one. And again, this and this, I'm not going to list these as a pair, because actually these two are what I would call essentially the same graph, that they're isomorphic. This is just, you know, it's like a Z shape, and here it's just turned sideways. So I'm going to draw that graph like this. This is the same graph. And then we also had this one, but as we said, this one was isomorphic to a previous case that we already covered. So this is my final list. This is a list of all the bipartite graphs whose complements are also bipartite. And I had better cut this off and start a new video.